I'm Ankur, and I'll be talking about preempt auto today. And so this is a new preemption model that is based on Thomas's work, Thomas Gleixner. Okay. And so we already do have enough preemption models, right? We have, depending on how you count them, we have 4 or 5 preemption models. So why add another one? So let me try and motivate that. So first of all, the preemptible kernels, you have the full preemption and RT, where you could essentially preempt at an arbitrary instruction, so long as it's safe. And the safety property of the preemptible kernels is basically established via preempt count, right? In addition, you have the voluntary preemption models where preemption only happens at these preemption points, and those are defined as these interfaces. Can't resched, might sleep, and there the safety property is not. The kernel does not know when it's safe to preempt. You have annotations, the preempt points, which tell you whether it's safe to preempt or not, right? And then you have preempt dynamic, which kind of combines all of these such that you can kind of switch between all of them, but the fundamental preemption models remain the same. All right, so just to motivate this, let me approach it from kind of where it sort of started for me. So I've been trying to clear like memory faster for a while, and eventually I came to a loop of this kind. So it's pretty straightforward. This is an x86 instruction rep store SP, and all that you're doing here is you're specifying in RCX the extent of the region, and you're clearing a gigabyte page, so that's the extent. And what this instruction would do is it would essentially zero that whole region. And on an AMD Milan system, this gives you something like 50 gigabyte per second, which is pretty good. As we'll see, what we actually get is much lower than this. And what that in effect means is that this instruction will execute for something like 20 millisecond, right? Because it's zeroing a gigabyte region, it executes for 20 millisecond, and it's done. It's an interruptible instruction, and it'll restart from that point in time. So it can actually you can take an interrupt in the middle. And what else? Yeah. So now let's see what actually exists in the kernel. So what the kernel does instead is, I mean, this is obviously not code that executes, but this is kind of a paraphrase of this code, which basically does clearing page by page, and a page on x86 would be 4K. So what it does is it basically calls conn resched, and then it calls the clearing routine, and so it would essentially execute a similar loop as on the last page, about 256K times or so, and the performance it gets is much lower at about maybe what 30% of or 35% of what you were getting with the when you were doing it in one sort of fell swoop. And the reason this loop or this code performs so much better is because now that the CPU knows how much what the real underlying extent is, it can do optimizations such as elide any cache line allocation, because there's no expectation that that any of that gigabyte region just written to would be in the cache, and so the CPU can not cache anything, and so this gets 50 odd gigabyte per second, while this one only gets about This one only gets about 19 gigabyte per second. And yeah, I mean, I think this is pretty straightforward. But the reason why you have to you do it, this way, is because the voluntary preemption models sort of necessitate calling Conry sked, every once in a while, and for a variety of reasons. The natural unit here is page size, partly because of high mem, and you had to choose a unit. So kind of page size is like a sort of sane sort of value for it. So yeah, I mean, this isn't really good. You could actually perform much better, but you have this awful performance. And this is not just for this code. This code is slightly special in that you have an underlying instruction that executes for a long time, etc. But if you look at the kernel, it will have all of these con resched calls kind of spread all over, and in a good case, it doesn't cost you any performance like it does here, but it still makes the code more complicated because you have to kind of break everything down into these bite-sized chunks. Plus, as I was saying earlier, this con resched is only needed for the voluntary preemption models. The full preemption model does not really need this, but the full preemption model will also pay this cost because the code is common, and you've kind of reorganized it into these bite-sized chunks, which are not really needed for full preemption. Okay, so yeah, I mean, this is just a summary of all the ways that you have a problem here. Con resched kind of assumes that an instruction runs for a short duration, which is, I mean, clearly not true in this particular case. And the assumption is there because con resched needs to be called synchronously. Full preemption also has its own mechanism of letting the scheduler know every once in a while that, oh yeah, you can switch if you want, but that mechanism is asynchronous, while here all that you have is a synchronous mechanism. And then the other problem with con resched is that there's no real good way of adding them. You typically add them kind of randomly, as you find soft lockups, splats, and so on. So I wanted to see how frequently we call con resched, and so this is sort of numbers from a kernel build workload, where I'm plotting the number of instructions between two successive con resched calls. And as you can see on the left side, and both of these axes are log scale. Yeah, as you can see, in this region, the frequency is pretty high, and that is after a con resched call between, say, 1,000 instructions or 10,000 or so. So we're calling this extremely frequently. Then you have the middle where this region where you do want to, and then you have this long tail where you execute a ton of instructions with no con resched calls in the middle. And ideally, of course, if you had a mechanism like con resched as we do here, you would want those to be evenly distributed. But I mean, that's kind of impossible because it's a dynamic execution kind of path. I mean, still, I wouldn't this is not a performance problem because a con resched call is pretty cheap. I mean, it's just a sort of a hot cache line lookup or a load, and then I think what would be a fairly well predicted branch. But I mean, aesthetically, this seems like just completely crap. Okay. So yeah, that's kind of one aspect of the matter. But are these con resched and might sleep, are they even like, good interfaces? And this is an example I kind of stole from Thomas. So, if you look at the mutex lock code, mutex locks can sleep, right? So it is annotated as might sleep, right? And of course, preempt voluntary turns might sleep into a call to con resched, which means that you can actually schedule out here, and that is the problem if you're in a nested mutex lock kind of situation, right? So say you acquired mutex lock A, and then when you try to acquire B, you it was contended or whatever, and so and somebody else wanted CPU, so you kind of go to sleep, and that kind of prolongs the period of time where you would be holding on to A, and that essentially just adds to contention. And the reason why con resched or might sleep can have behavior like this is because they don't actually carry any context with them. They have no idea what context they're executing in, right? So which means that that you could actually get into a situation like this because B does not know that it is in a context, a nested mutex lock context or something like that. Okay, so right, so this is basically what I just said here. All the ways that these explicit preemption points are kind of bad, and so let's see what we can kind of do about them. So just to kind of rehash, how this kind of the whole thing works is in the kernel preemption. You cannot force preemption in the kernel. You cannot force switching out of a task, right? So if the kernel decides that, oh yeah, the current task is done, we need to switch to a different task on the route, all that it would do is it would set this need resched flag, and this would the kernel, the scheduler would know this in response to a timer tick or a wake up or what have you, right? And then it would return to whatever was happening before that, right? In the full preemption context, now you would check this flag at, say, the next preempt enable or at when you return from an IRQ, which in this case could be the wake up, right? And at those places you would check if it is safe to preempt by evaluating this flag and preempt count, and if it is safe, you would switch. If not, then you can always eventually preempt at exit to user, right? And full preemption works like this because you want to minimize latency, so you do this as soon as possible, right? Voluntary, on the other hand, does not have a preempt count at all, right? So what it has are these two, con resched and might sleep kind of hints. And one reason why voluntary preemption methods do it like this is because they have this notion of run to completion. And the idea is that the kernel has no real way of knowing when a task is reasonably complete, right? So this hint from the programmer, who from the code that is executing in a loop or whatever, has a clear, well-defined notion of, oh yeah, this iteration is complete. So this is a good time to schedule out rather than, or to preempt rather than this, some other time, right? So the scheduler has essentially offloaded the decision, the completion decision to the running code, and that sounds reasonably sane, right? So let's see if we can kind of get the same thing with this new preemption model, preempt auto. So what preempt auto does is it adds it keeps the preempt count, from the full preemption models, and then it adds a new preemption level. So in addition to the need resched, you also add this one called need reschedule lazy, and the main difference between both of them is, when are they checked? So need reschedule gets checked at sort of the usual spots, but reschedule lazy is only checked when you're exiting to user, right? And so that's kind of the mechanism part, and the policy of when you would set which bit essentially would determines or based on the preemption model. So you can kind of approximate a preempt none like preemption model, voluntary, full, just based on when you set these bits. So so let's say we're doing preempt equal to full under preempt auto. So you always just set this need reschedule bit, right, and check that the usual places, right, these three, right, and this is exactly equivalent. This is exactly equivalent to the preempt full model, right? So essentially nothing has changed here, right? Which is what we want. Now, if you're looking to do something like preempt none, then I mean, this is quite an elegant idea. That the whole point of preempt none was to run to completion. So why don't you actually just run to completion? And you just kind of trivially get that by checking by the scheduler setting this bit, whenever it decides a reschedule needs to happen, a preemption needs to happen, right? And the only point you are going to check it is at exit to user. So at exit to user, it's clear that whatever the task was doing is done, and so you just very straightforwardly get run to completion. Okay, then yeah, for preempt equal to voluntary, that's a little, I'm not super happy about it right now, but right now what we do for that is that it's run to completion unless a higher scheduling class task awaits. And if there's a higher scheduling class task around, then you just set the need reschedule bit. If not, you just set the lazy bit. And these are checked at the usual spots, and actually that's all you really need to do. Yeah.
Just this idea of the preempt lazy, it's still the same thing that we have on the preempt RT, right? In this voluntary, is the current behavior that we have there or not? Yes, just to introduce to the people, this idea of this schedule lazy, it exists on the preempt RT as a method to try to keep a little bit more of throughput for the. Yeah.
So
yeah.
No.
So the original version of it was made to regain throughput for non-real-time tasks. So if you had scattered tasks, instead of setting the preempt bit, I set preempt lazy, and then gained more throughput because they could run actually to completion unless there was a real-time task. So what I didn't realize back then, that this would be actually the replacement for the whole cont resched nonsense. And when Ankur tried to get the clearing running,
right,
I said no. So we run RT now with a modified, a pretty much a lost version of Ankur's stuff, and it replaced the old preempt lazy mechanism I had. So
I didn't know that.
It holds up pretty well.
Good.
Cool.
Yeah, one thing I just also want to add on to that part, but the throughput part was what really it plays to my next comment on this. It helps with lock contention. So with the RT stuff, a lot of times what we found was because RT basically makes all spin locks into mutexes, we were getting preemption all the time, which meant that if you preempt while holding a lock, you're much more likely to have contention on that lock. And by saying, hey, the lazy was originally to say, hey, don't preempt if it's not if a non-real-time task is waking up or if the scheduler click ticks, instead of, saying, hey, your time's up on the scheduler, schedule out. We actually said, oh, you're holding a lock. Wait until you release the lock before we schedule out, like a spin lock one, not a mutex, but a spin lock. So that actually helped a lot of the throughput. And I'm excited about this because I want to extend this into user space, so that user space could actually set a RSeek bit to say, hey, I'm in a critical section, I have a lock or whatever. And if need resched lazy is set, if you have this bit set and need resched lazy's set on exit to user space, it will ignore scheduling out there and let you go into user space longer. And when you hit that, you have to do a system call. Once you clear the bit and do a system call, you'll automatically schedule out.
Peter didn't turn into mute.
Well, he's seen the code.
Yeah, so you cannot rely on user space being sane. And I mean, we've had this discussion and patches and everything.
Well, the thing is, exactly, the beautiful about this part was the fact that it would only get one more tick. And if it were tried to abuse it, if we have eligibility enabled, the VDF scheduler, if some task tried to abuse this, it would start getting huge negative lag, and it will actually start throttling itself. So if it tries to keep it set, the scheduler itself would actually punish it
over the long term.
Yeah. So basically you could get a little bit away, but the more you use it, the scheduler will just start throttling you more, because you're going to be using more, because the lag will start building up. So it self-corrects.
Right, but I mean, that seems like a good argument to me, but that clearly does not convince Peter, and I'm kind of curious why. All right, so let me go to the next slide. Oh yeah, sorry.
Are you speaking? I wanted to tie back to Stephen Thomas, who touched on the what does it mean to kill throughput with contention, and this Thomas said it at kernel recipes the last November. It's also in the proof of concept, etc., which is preempt a task which is holding a lock, so it's already. And so this is a central concept why a lot of people, as Thomas said, the kernel recipes think that preemption is because the overhead of context switches, right? So for me, I turned my perspective and said, I didn't realize that. That's rather deep and profound. But then Gautam, with his analysis of that star, he was, Netflix, Nginx, sorry, the Nginx web server wasn't holding any lock, but preempting it was still killing the benchmark. So that's a kind of a additional. It's a different situation. Like
it could be,
right.
I guess with locks, you have a well-defined pattern, whereas here you're just relying on the relative average VRun times of the two tasks, so which is non-deterministic. With locks, you know for a fact that you're holding a resource, and if you're context switched out at this point, you're probably blocking the others.
See.
All right. So running to completion has a problem though, and that is that you might run into a CPU hog, and an example of a CPU hog would be, for example, a gigabyte, somebody zeroing a gigabyte page or whatever, right? And so how do you deal with hogs which do not actually exit the kernel, or maybe don't execute preempt enable or whatever? And so, it's a pretty straightforward mechanism. So if a task does not relinquish CPU, you get a timer tick. And at the tick, you have set, need reschedule lazy, with the expectation that, soon enough, this task would be done with whatever it's doing. It'll, execute exit to user, and switching would happen. If it does not happen, then at the next tick, and that's what we're using right now. But that's just you can change the sort of width of the interval. But at the next tick, you can just straightforwardly upgrade. If need reschedule lazy is set already, upgrade it to need reschedule, and that would send an IPI, if needed, if it were remote, for example, and at the next at the exit of the timer tick, or at the next preempt count check, you basically reschedule, and that basically forces preemption, and you kind of done. So that's actually all that you really need to do under preempt auto to kind of get this working. So it's pretty straightforward. It's relatively well contained. There are a few things I'm not super happy about. One is, as I was alluding to earlier, preempt voluntary is quite thin, and semantically it's quite different from the sort of baseline preempt voluntary that we have right now. What preempt voluntary, as it exists in the kernel now, does is it gives you these additional preemption points, right, which would affect all tasks, right? But the preempt voluntary under auto right now would really change behavior only if there were higher scheduling class task present. And I mean, I have some ideas about experimenting on this, but the thing is, I'll come to the performance numbers. The performance right now seems pretty good. So I'm honestly looking for suggestions of tests and things where we have maybe regressions or something to try different policies.
Yeah, I wanted to confirm that I understand this correctly. I'll also offer some history lesson, because I looked at this, how the preemption model, and so what it seems to me that you are trying to, and you confirm that or not, you're saying, well, I need voluntary to look different than none. Like I need voluntary to look a little more preemptive than none.
Yes.
So where do I put, like, how do I give it this extra juice? And then you have this ingenious idea, say, okay, the higher scheduling class, and then I'm going to schedule. That seems fair, but I share with you, I sympathize with you that what can you do? I mean, preempt voluntary is, and here is the history class, an historical accident, in my opinion, because looking in the history of the Internet Archive, etc., 1991, Linus Torvalds made Linux and preempt none. The year 2001, Monta Vista, an engineer named Nigel, I don't remember the last name, makes the fully preemptible patch, right? So we have none, and then in the year 2000 we have full preemption. It didn't really work immediately. The maintainership of it was then Robert Love, who carried on after Monta Vista.
So, hang on. Yeah, even if it is historically how it came to be, people use it, and clearly the way it evolved is reasonably useful, right? So yeah, there's no harm in figuring out ways to kind of,
right?
Yeah.
Yeah, but it actually voluntary, it's not that important anymore as it used to be when it got introduced. So one of the issues which was back then notoriously problematic with none interactivity on the screen. And that was pretty much solved with voluntary, but we are 20 years forward, and so many things have changed. CPUs have gotten extremely fast,
Right.
and so a lot of these problems do not exist anymore. I mean, you don't run your desktop on a uniprocessor with 400 megahertz anymore. That's a totally different thing.
Right.
And if you look at the relevant workloads, the big machine workloads, voluntary is probably counterproductive in the very end.
Okay, interesting.
Yeah.
So if you can really get rid of these stupid points and I did some experiments with analyzing how often the voluntary points give you a false preemption, and under certain database workloads, that's quite often because it's just wrong to do at that point.
Okay.
And the enterprise systems run a lot with voluntary.
Yeah.
But some of them actually, and that's why we have the whole dynamic switching now. For some workloads, they go back. The users want to go back to none, because exactly to avoid the extra context switches, which are stupid in many places. Okay. Most of them are caused by might reset or might sleep, which is sprinkled all over the place. And it would have been interesting because your graph before from conrisket was against none, right?
That was against none.
Yeah.
Yes.
Did you take such a graph for a voluntary?
I did. Yeah.
Yeah.
It's not in the slide, but
yeah, but it's probably even worse than
yes.
Yeah, exactly. That's the point. So I'm not truly worried about the difference between voluntary and at the very end. If there's stuff which really needs this, then it would now become a problem of the scheduler to decide when to set if need reset instead of the lazy bit.
Right.
And if you have exactly these things where you say, okay, this is the sporadic event which needs to get on the CPU fast, but then this is a scheduler internal decision, and we can tweak it here, and we don't.
Right.
But we don't have to play the silly games of throwing all the voluntary preemption points throughout, sprinkling them throughout the kernel.
Yeah. So basically, you're saying that the thinness of it might be a feature, not a bug. The fact that preempt voluntary will be extremely thin. Yeah. Okay.
Yeah, I rather consider it a feature.
And it would bring to the scheduler the decision to, or the opportunity to optimize those cases and to use the risks on the scheduler and not relying on the risk that the developer thought when he put the commit reschedule.
Yeah, I know. I looked at quite some of the conrisket sprinkled cases, and
yeah, it's just
I'm pretty sure that 25% at least are completely bogus.
Yeah, because they don't understand the scheduler. Yeah, it's a good thing to move this decision to the scheduler.
Cool.
Yeah. So one thing that I want to add on what Thomas was saying. So in the Ubuntu kernel, historically, everything, most distro opted for the preempt voluntary because we were like super worried about regressing server workloads. So recently, in the latest 2404, I made the proposal to like change the hertz from 250 to 1000 and also change preempt voluntary to like fully preemptible kernel. We did the change for config hertz. My proposal to change to fully preemptible wasn't approved, but we ran some benchmarks, and the server workloads, like typical server workload, was actually performing better with fully preemptible kernel versus the voluntary. So like things have changed. Like servers are also, I mean, even typical server workload now cares more about interactivity, probably responsiveness, than it used to be a while ago. So
Okay, let me talk to you after. It might be interesting seeing some of those numbers. Cool. Okay, and a couple of others is that need reschedule. You would if you're say doing a wake up from a remote CPU, would result in an IPI, and need reschedule lazy. You can kind of get rid of, and so there's one case which I was a little worried about. I talked to Frederick after that, so less so now. But under no hertz full, for instance, you also do not have a timer tick. So yeah, it seems like a slightly complicated interaction. But of course, no hertz full, the tick is only dropped when you have just one task on the run queue. So I think it's fine, but I'm
Yeah, that should be a known problem, because the tick is stopped when you have the single user space thread,
right.
and that can compute forever. And then if you get a second runnable, I mean, you go anyway through exit to the user, and then lazy is just evaluated, and it's not a problem at all.
Right, and the tick would restart if you woke up another task, right? Yeah.
So I don't think it's a problem.
Cool. Okay. All right. So the current status is basically that I posted V2 recently. The performance so far should be fine. I mean, I'm actually quite surprised by not having regressed on anything. There's one regression that I know of which we're debugging, which is on PowerPC. But yeah, otherwise, most things are more or less within margin of error. And this is kind of macro benchmark with some people in Oracle kind of run, and this is like a big database server talking to, like, I don't know, 10, 12 storage nodes, and so you have a large number of clients basically doing some sort of SQL queries or whatever. And I'm honestly not quite sure what's going on there, but I do know that higher transactions are kind of better. So here you don't always get higher. There's one case which sees a decent improvement, but it's either negative or within margin of error. But I mean, it seems like it's kind of holding up, at least so far. Right, and so this is kind of just going back to where I sort of started on this whole thing, which is getting rid of con resched. And I think that is some time off, because everybody needs to be, I don't know, convinced before that they can actually switch to this sort of new preemption model. And before that, there is a bunch of things in the kernel that we need to kind of do. One is that all the platforms need to be supported. Most of it looks straightforward. You just basically need to define a new flag and check for the flag at a couple of places or etc. But there are some architectures that Thomas calls museum pieces, alpha and so on, which don't support preemption at all. And here we do depend on the preempt count being at least available on the CPU. Then in recent years, live patching, just to kind of get stable stack unwinding, depends on con resched, even in fully preemptible kernels. So yeah, that I mean, we need to figure out a solution. And of course, there's the sort of slightly open-ended problem where you need preempt auto to perform well on a large enough variety of workloads before you can kind of say that, oh yeah, people can switch to it. And I think, yeah, that's all I have. I'll take any more questions. Thomas.
Not a question, but more a remark to your opens. I mean the museum's pieces. I'm not really concerned about that. So I mean we will not replace the existing trinity of non-voluntary and full immediately with auto. They have to coexist for a while before we can rip out the old crap. Obviously to address the other bits and pieces. I mean, live patching, it should be not a big deal to come up with a mechanism to park the stuff in well-defined places.
Yeah, I was talking to Josh Primbuff, and he and Mark Rutland said that S-frames, which I think some people are working on, might kind of be the way to get a dependable stack unwind.
Yeah.
On ARM.
I think this is a solvable problem, and the performance thing. As long as your stuff is in the plus, it wins a percent here and it loses a percent there range. I mean, I haven't seen the standard deviation for it yet. So this is pretty much in the range where we operate on every other kernel release anyway. So
Right.
because so the stuff has become so sensitive in terms of code placement, in terms of what the compilers do, and so I'm not worried about it. I mean, if it's you lose constantly 10% or 5% or whatever, then you have a problem. I mean, the PowerPC thing actually needs to be investigated.
Yeah.
But that's an obvious big thing where they lose, and maybe it's just the PowerPC ports which they screwed up.
Yeah, I think there's something screwed up there because they're seeing like 2x the number of context switches, and on the same workload, I'm not seeing anything like that on x86. So yeah.
Yeah, so probably their logic of evaluating the bits is
Yeah, I think
kinda
something's messed up there. Yeah.
bonkers. They will probably figure it out.
Yeah. All right.
Peter, what's your take?
I think the patches as posted are a hot mess, but the idea is fine. We'll fix it. I mean, it's not a problem.
Cool. All right. Thank you, everybody.